In this video, we will focus on regression. Regression uses a model to allow us to evaluate and anticipate the possibility of values that are outside of our sample that may be present in the population. We will explore this with more than one predictor and compare the usefulness to make decisions. We will also look at other methods to predict the likelihood of events. Simple linear regression is where managers are seeking to make decisions based on relationships between two or more variables. When we are evaluating something and we get a model for it, which will be clear in a minute, we can do additional things than understand the sample we have data on. We can extrapolate to other data. In some ways, it is like looking at the future. We will be looking at dependent or response variables that will be predicted by an independent variable, also known as the predictor variable. Simple linear regression uses one independent and one dependent variable. The relationship will be described by a straight line. That's why it's called simple linear regression. There are other techniques that you can use to evaluate different types of relationships. If we use more than one independent variable, we call this multiple regression. We will look at both simple linear regression and multiple regression today. This equation describes how something we are interested in, the dependent variable y, is related to an independent variable x in this regression model. This is the equation of a line, basically. We have b0, which is the y-intercept of the line, and we have b1, which is the slope of the line. Then we have x, which is the independent predictor variable. By plugging in the numbers, once the line is established, we will be able to predict for y. So let's look at each of those components in detail. The intercept is where this line connects to the independent variable on the y-axis. If there is no relationship, b1, the predictor variable, will be 0. If it is 0, then our predictor will also be 0, and therefore our response variable will be equal to the mean of the dependent measure, because that is the best variable we have. So if you can imagine, if b1 is 0, then this whole component is 0, which means that b0, the y-intercept, has to equal the mean. If the value is non-zero, it will adjust the y-intercept. Now let's look at the slope, b1. This one is a little bit more involved, and we will look at it in just a minute. So first, let's look at what a regression line looks like when it's finished. So here we have 3 possibilities. In each of the possibilities, you have the x-axis, which is the independent variable, and the y-axis, which is the dependent variable. And the line may be going up, going down, or horizontal. If it is going up, it is positive. Going down, it is negative. Horizontal means there is no linear relationship. Now, this may look familiar from the correlation video, and that's because regression and correlation are very much related. And this is beyond the scope of this class, but if you're interested, we can talk about it. Now, here's an example of using simple linear regression, where we have data from web ads that are viewed and the website visits. We have a few data points and we have some statistics from obviously a larger population. And here it shows you how to calculate the slope, the y-intercept, and how to set up your model. And this is the important part, because once we have our model, we can plug in values and we can start predicting for values that we did not sample in our data set. Now, the way we would read this is that for every 1 unit of change in x, y will be changed by the sum amount. So in our example, we could say for every web ad viewed, website visits increased by 15. Here is what a scatter plot would look like when the regression line has been fitted. So let's look at this in a bit more detail. On the x-axis, we have web ads. On the y-axis, we have the web visits. The dots are the actual observations that we have in our data set. The blue line is our regression model. And the regression model that we have built is also called the best fit line. It's the best fit line because it minimizes the squared residual errors. Okay, so that sounds like a mouthful. So let's explain what that means. What a regression line is actually based on is the prediction of every value that is possible within the range of the observations. The equation figures out the sum squared error residuals, this SSE, which is essentially the difference between what has been observed and what has been predicted. And what the regression line is the minimization of that difference in total. So the line is the best fit because no better line could be drawn that would minimize the difference between the actual and the prediction. That is why it's called the best. Now, there are some other measures to keep in mind, and one of them is the sum of squared regression, SSR. And this is the difference between the regression line, what the regression line predicted, and the mean of the dependent variables. So if we only took our observations and we took the mean, we would get a measure. And what we are trying to find out is how much better is the regression compared to just simply taking the mean. The final calculation we need to understand is that we also need to look at the mean of the dependent variable for every value that we have available. This is our null hypothesis. The null hypothesis states there is no relationship. And so if that's the case, we have a horizontal line, which would be the same as the mean. That's the null. The null hypothesis is the mean. The sum of the squared total error, right, SST, is the difference between what was observed and the dependent variable mean. So the difference between what was observed and the mean. We are trying to improve from just using the mean. So what we have just described is that regression is basically partitioning the sum of squared total error into the sum squared regression and the sum squared error. So we want to maximize the sum squared regression because that tells us we are explaining how much we are explaining of the data. And we want to minimize the sum squared errors. And in our example, we are explaining 100 out of 114. Here's another way to represent the same information. One of the important benefits is that we can use this to calculate the coefficient of determination, which is this ratio. So we are using the variables we have just computed into a ratio. And this ratio is the coefficient of determination, or squared. We can interpret that ratio as the total variability that is accounted for by the regression from our data. And in our example, we can see that the ratio equals to 0.8772. And the way we can interpret that value is by saying that 87.72% of the variability in the number of website visits can be explained by the linear relationship with web ads viewed. In other words, web ads viewed accounts for 87% of the variance in website visits. With simple linear regression, if we only have one predictor in our model, if we take the square root of the R squared, it will give us the coefficient correlation. And in our example, this would be 0.9366. There are some assumptions with regression. The first one is called normality, where we are concerned with the residuals being independent and normally distributed. There are tests available to check this. The second assumption is something called linearity. Here we are assuming that the relationship between independent predictor variables and dependent variables is linear. The third one is homoscedasticity. Here we are concerned that the variance of residuals is equal for all points. Sometimes these assumptions can be violated, and the validity of the analysis would not be impacted. However, it should always be noted. For regression, at least in our class, it is also important to remember that the dependent variable must be a ratio or interval. Our independent measure must also be a ratio or interval. There are other ways at looking at relationships between nominal and categorical values, but those are beyond our class. Now, let's briefly look at residual plots, one of the assumptions. Here we are looking at the standardized Z predicted value versus the standardized residuals. And if our plot looks like this, it indicates consistent variance. But if it looks like this, and the spread exceeds plus or minus 3 standard deviations, then this indicates non-constant variance, and we are violating one of our assumptions. Okay, finally, let's briefly look at multiple regression, which considers more variables or factors and thus obtain better estimates than is possible with simple linear regression. We can add variables to have better predicted values. It looks a little bit different, but we are just adding independent variables and so the model is expanding. The formulas for regression coefficients require matrix algebra, so we usually let the software calculate this for us. And all the values represent an estimate of the change in our dependent measure y corresponding to 1 unit increase in x. And this is the very important part. This is true because we hold all other independent variables constant. Here's a note of warning though, because the more variables, independent variables we add in a model, even the ones that are not statistically significant, causes the prediction value of our model to increase, even though our model may not actually be stronger. And so it is best practice to adjust the R-squared to compensate for the number of independent variables added to the model. It is also good practice to be careful about independent variables being correlated amongst themselves, because if they are highly correlated, it is not possible to determine the separate effect of any particular variable on the independent variable. So we should avoid this. There are other techniques available. For example, if your relationship is not linear, but is in fact curvilinear. In this case, we can use a regression that's made specifically for curvilinear relationships called a quadratic model, and it works the same and is interpreted the same way. And another case is if we have dichotomous dependent variables, we can use a log linear regression. And if we're using count data, we can use the Poisson regression. So in summary, we can use simple linear regression to evaluate how one variable is related to a dependent variable. We can use multiple regression to evaluate more than one variable and how it's related to a dependent variable. And for any other type of variable that's not continuous and scaled, we can use other types of techniques like logistics and Poisson regression.